Chapter 7.2, Absolute Value Functions. Example, graph the following functions on your calculator, one at a time, and state any patterns you observe. We have y equals 2x plus 5. Let's graph that. And we get this. Let's do a little sketch here. It's not going to be perfect, just a quick sketch. Looks something like this. Now let's go back to our y equals and enter the absolute value of 2x plus 5. To get absolute value, we do math. We go over to num, and then we push number 1. For the Casio calculator, to get absolute value, you push option, then you push F5, and then you push F1. So inside the absolute value, we are entering 2x plus 5. And we graph that. And what do we notice? We see that our graph looks to be on top, or part of our graph, the right side here, this side, seems to be on top of our original graph, 2x plus 5. We can tell that it's on top if we go back to our y equals. If I hit enter on the absolute value one, it'll turn it off. So that means when I graph it, I won't see it. And then I can see my blue line again. So now I can see the blue line up here. And if I go back to y equals and I go back to my y2 and I hit enter again to turn it back on, graph, and again, we can't see it. So we know it's there. It's just being covered up by the absolute value function. Okay, so our absolute value function looks something like this. Where it goes over top of our original function for part of it, and then it's got this V shape to it. So this linear is y equals 2x plus 5, and then this part, the V shape, is y equals absolute value of 2x plus 5. Part B, y equals negative 4x plus 3. Graph that, and we get something that looks like this. Go back to our y equals, down, absolute value, math, over to num, number 1, absolute value of negative 4x plus 3, graph, and again we can see that it's on top. So the portion that's above the x-axis, our absolute value function mimics that portion, so it lays on top of that portion. And then we have this other part, this V shape. Where do you think that other part is coming from? If we look at the bottom part of our original function, the linear, negative 4x plus 3, it looks like it's just a reflection of that across the x-axis. Okay, that's a reflection. This here is y equals negative 4x plus 3, and this one is y equals absolute value of negative 4x plus 3. So why do we think it's being reflected up into the positive y's? Think about, what does absolute value mean? What did we talk about in the last section? It means how far away from 0 a value is. So whether it's negative 7 or positive 7, the absolute value of negative 7 and the absolute value of positive 7 are both 7. Absolute value is always a positive number. So it makes sense that the absolute value graphs are in the positive y values only. Okay, so any y value on a graph that is negative, that is down here below the x-axis, when we take the absolute value of that function, it's going to turn into a positive, so it's going to be reflected up above the x-axis to that reflected line that we have there. C. Now we have a quadratic. Go back to y equals. Clear that, clear that. We have x squared plus 4x minus 6. X squared plus 4x minus 6. Enter. And it looks something like this. So what do we think the absolute value of this function is going to look like? Anything that's below our x-axis is going to be reflected up. So this portion down here that's below our x-axis is going to be reflected above the x-axis. So it should look like this. Let's see. Go down, enter absolute value, math, over to number 1, absolute value of x squared plus 4x minus 6. Graph that, and that's exactly what the red line looks like. It is reflected up, so the two parts that were positive y values stay the same, and then the part that was below the x-axis that had negative y values gets reflected up into the positive y value, so reflected across the x-axis. This part is y equals absolute value of x squared plus 4x minus 6, and the quadratic was y equals x squared plus 4x minus 6. Last one. Another quadratic. Clear this, clear this. Negative x squared plus x plus 1. Graph that, and it looks something like this. So using our knowledge so far, what do we think this is going to look like? Well, any piece that is below our x-axis has negative y values is going to be reflected up across the x-axis, so it's going to have positive y values. So this part will be reflected up here so that the y values are positive. So these two arms get reflected up. This part, the vertex is already in the positive zone, so that's going to stay. So we would expect it to look like this, where that arm's up here. This portion's the same as the original function, and then that arm's reflected up. So kind of like a W. Go back to our y equals, go down and enter absolute value of negative x squared plus x plus 1. Graph that, and that's exactly what we get. We have the left arm is reflected up. The middle portion is the same, and the right arm is reflected up. So that is y equals absolute value of negative x squared plus x plus 1. And the parabola is y equals negative x squared plus x plus 1. So what did we see from these graphs? Get rid of this. Okay, what did we see from these graphs? What knowledge can we take away? Number 1 is that our x-intercepts are the same for y equals f of x and y equals absolute value of f of x. We see that on B here, our x-intercept is here. That point is the same on both functions, and then anything below that gets reflected up across the x-axis. Here we have our x-intercepts are the same. Anything below that gets reflected up across the x-axis. D, we have the x-intercepts. They're the same on both functions. Any part below that gets reflected up across the x-axis. What are points called when they're the same on the original function and the transformed function? Those are called invariant points. The next thing we saw is where the graph of f of x is positive, so positive y values, the graph of absolute value of f of x is the same as the graph of f of x. Okay, so graphs lie on top of one another. And then the third thing, so graphs lie on top of one another when the original function is positive, but where the graph of f of x, our original function, is negative, so negative y values, then the graph of absolute value of f of x is reflected across the x-axis so that absolute value of f of x is positive. So a piecewise function, if we wanted to write an absolute value function without using the absolute value symbols, we would have to write two separate functions. So when we do that, it's called a piecewise function, a function composed of two or more separate pieces, each with its own domain that combine to define the overall function. The absolute value function y equals absolute value of f of x is equivalent to the piecewise function y equals, we do a curly set of brackets to include both of our pieces. We said that when f of x is positive, then our absolute value function is just f of x. So the piecewise function would be f of x for f of x greater than or equal to 0. And then when f of x is negative, the absolute value function is the reflection of that across the x-axis. And if we think back to chapter 3.4, a reflection across the x-axis was represented by a negative a value. So if we have negative 1 as our a value, then our function would be negative f of x, and that would be for f of x less than 0. And then we close our curly brackets. Example, write y equals the absolute value of negative x plus 1 as a piecewise function. First thing we want to do is to draw a quick sketch. And you want to sketch starting with just the function inside. So f of x would equal negative x plus 1. So we just drop the absolute value symbol and we do the inside. So negative x plus 1, that has a y-intercept of 1 and a slope of negative 1. So as we move to the right, it's moving down. So it's going to look something like this. And then we can use that to draw our absolute value function, because where that function is above the x-axis, which would be here, then our absolute value function lays on top of it, and where the function is below the x-axis, which is here, that portion's going to get reflected up across the x-axis. So our absolute value function will look like this. Step number 2, I need to identify the x-intercept or intercepts if there's more than one. Remember, our x-intercepts are the same for the original function and for the absolute value function. So I'm going to use the original function f of x equals negative x plus 1. For the x-intercept, we sub in 0 for y. So instead of f of x, I have 0 equals negative x plus 1. And then I want to isolate my x. So I'm going to add x to both sides, and I get x equals 1. So my x-intercept is at x equals 1. Step 3, I want to label pieces of the absolute value function. The two labels would be, one part of the function is the same as f of x, so we'll label it f of x, and the other part would be the reflection across the x-axis of f of x, which is called negative f of x. So the portion that lies on top of the original is this here. That portion is f of x. It's the same as the original. The piece that is not on, that is reflected across the x-axis, is this piece. So that's the negative of f of x. Step 4 is to write the piecewise function. So we have y equals curly bracket, and then f of x, so we're following this format, f of x for f of x greater than or equal to 0. That's going to be an x value that determines when it's greater than or equal to 0. So what is f of x? What's the function f of x? That was negative x plus 1. It's just whatever's inside your absolute value symbols, that's your f of x. So I have negative x plus 1. When is this function greater than or equal to 0? It's greater than or equal to 0 over here, which is when x is less than or equal to 1. Okay, so it's always going to be defined based on our x-intercepts. In this case, it's a linear, so there's one x-intercept, and the graph of f of x is positive left of that. So we write negative x plus 1, which is f of x, for x less than or equal to 1. The negative portion, this portion here, this is the reflection of this part of f of x. So it's negative f of x, which is negative bracket negative x plus 1. So you just put your f of x in brackets and you put a negative in front of that. When is that defined? What x values is that defined for? Well, we want to look at our x-intercept again. The portion of the original function that is below the x-axis is to the right of the x-intercept, which is 1. So when x is greater than 1, there's our piecewise function. Y equals negative x plus 1 when x is less than or equal to 1, and negative bracket negative x plus 1, the reflection of negative x plus 1, when x is greater than 1. For the following functions, A, determine the x and y intercepts, B, sketch the graph, C, state the domain and range, and D, express as a piecewise function. First one is 3x plus 1. Determine the x and y intercepts. How do we determine the x-intercepts? We sub in 0 for y. So our function here, this is the absolute value function. Our f of x would be 3x plus 1. Just drop the absolute value portion. So I'm going to plug in 0 for y and 3x plus 1. 0 equals 3x plus 1. And then I'm going to solve for x. Subtract 1. Divide by 3. X is negative 1 over 3. Y-intercept. Sub in 0 for x. This time we have y equals 3 times 0 plus 1. This is 0. We have y equals 1. Part B, let's sketch the graph. So we know that our y-intercept is at 1 and our x-intercept is at negative 1 over 3. So about here, we'll say. So our graph is going to look something like this. That graph is y equals 3x plus 1. Now we want to do the absolute value of 3x plus 1. So how does that look? Well, anywhere above the x-axis, our graph is the same. So our absolute value function is going to be on this portion of the original graph. Anything below the x-axis, which is this portion here, is going to get reflected up. So it's going to go this way. So quick sketch, something like this. This one is y equals absolute value of 3x plus 1. Part C. State the domain and range for y equals absolute value of 3x plus 1. Domain would be what values of x are valid for this function. We can plug in any values of x. So x such that x, e, r. Range, what values of y are valid for this function. Absolute value is always non-negative numbers. So y such that y is greater than or equal to 0. Y, E, R. So all real numbers that are greater than or equal to 0. And then D expresses a piecewise function. Y equals curly bracket. Start with the function f of x. So just the part inside the absolute value, which is 3x plus 1. Where is our absolute value function the same as that function? What values of x? That was when our x values were greater than or equal to the x-intercept of negative 1 over 3. That portion of our function 3x plus 1 and absolute value of 3x plus 1 were the same. So the absolute value of 3x plus 1 is the same as f of x equals 3x plus 1 when x is greater than or equal to the x-intercept of negative 1 over 3. And then we do the negative. The piece that gets reflected up is negative f of x. So negative bracket 3x plus 1, close bracket. When is this the case? When x is less than our x-intercept in this case. That was the portion of the original function that was below the x-axis. So that's the portion of the absolute value function that gets reflected. So for x less than negative 1 over 3, and then close our curly brackets. There's our piecewise function. Last one, y equals the absolute value of x squared minus x minus 2. F of x would be just what's inside the absolute value, x squared minus x minus 2. Part A, find the x-intercepts and the y-intercept. It's a quadratic, so we're likely to have 2 x-intercepts this time, although we could have 0 or we could have 1. Sub in 0 for y. 0 equals x squared minus x minus 2. Let's factor. 0 equals two numbers that multiply to negative 2 and add to negative 1 would be x minus 2 and x plus 1. Negative 2 times 1 is negative 2. Negative 2 plus 1 is negative 1. And then we solve for x. When is x minus 2 times x plus 1 equal to 0? Well, it's when x minus 2 equals 0, which is when x equals positive 2. And also when x plus 1 equals 0, which is when x equals negative 1. For the y-intercept, we put 0 in for x. We get y equals 0 squared minus 0 minus 2, which just gives us y equals negative 2. Next is graphing. So plotting our points, we have x equals negative 1 as one of our x-intercepts, x equals positive 2 as the other, a y-intercept at negative 2, and our quadratic opens up because it has a positive a value. The a value would be positive 1 because it's x squared, so 1x squared. So it's going to look something like this. There's a quick sketch of our function f of x equals x squared minus x minus 2. How is the absolute value function going to look? The parts of f of x that are above the x-axis, so have positive y values, are going to stay the same. They're going to be exactly the same on our absolute value function. The portion of f of x that is below the x-axis, so has negative y values, is going to be reflected up so that it has positive y values. So it's going to look something like this, like kind of a W. Let's draw it. These portions are the same. They're on top of f of x. This portion is reflected up to be something like that. So that's our y equals absolute value x squared minus x minus 2. Part C, domain and range. Domain, again, what x values are valid for absolute value. We can have any x value for absolute value, so x, e, r. And range, again, we're always going to have non-negative numbers, so y is greater than or equal to 0, y, e, r. Part D, express as a piecewise function. Y equals f of x is what's inside the absolute value, so x squared minus x minus 2. When is it the case that the absolute value function is the same as the function inside the absolute value? In this case, it is this portion. So when x is less than or equal to our x-intercept of -1. And also this portion, which is when x is greater than or equal to our x-intercept of 2. So when x is less than or equal to -1, and when x is greater than or equal to 2. Those are the x values that are going to make our absolute value function the same as the function x squared minus x minus 2. Next is, when is it a reflection of f of x equals x squared minus x minus 2? So that would be negative bracket and then f of x inside, so x squared minus x minus 2. When is this the case? Down here, which is between the two x-intercepts. So when x is greater than -1, but less than 2. For x greater than -1, so -1 is less than x, which is less than 2. That brings us to the end of Chapter 7, Lesson 2.